Hi everyone, my name is Bliek and I will present our work, which is a submission to the GECCO Industrial Challenge, together with Guijt and Rickard Karlsson. In this challenge we have a hospital simulation that contains 29 continuous variables, and the simulation takes some time to run, after which it produces a scalar output, and the result is to minimize this output. We make use of surrogate models to optimize this simulation. And the way this works is the surrogate model approximates the relation between input and output, and then it uses this relation to suggest a new input point to try. And over time, as the approximation becomes more accurate, it will suggest better and better results. The surrogate model that we used is called a random ReLU expansion. And ReLU stands for rectified linear unit. Now this model has the following formula, where it consists of a weighted sum of basis functions. This is the rectified linear unit, a common function used in machine learning. And important to note here is that some of these parameters in the model are chosen randomly. And the reason for that is that it is a very efficient way of treating these parameters. You don't need to optimize them with gradient descent, for example. But also there's good theory available on randomly chosen weighted sums of basis functions. The only parameters that we do train are these C parameters. And the reason for that is that our surrogate model depends linearly on these parameters. So we can make use of linear regression techniques, such as recursive least squares. After training, we use our surrogate model to find a good solution, and this is done with a continuous solver. In this case, the LBFGS solver. It finds the minimum of the surrogate model, and then we add a small random perturbation to the found solution, just to add a little more exploration to our method and to avoid getting stuck in local optima of the surrogate model. In this challenge, the algorithms were only allowed to run for 200 iterations. So we compared different algorithms with this limited budget, and we reported the lowest objective value after averaging over 5 runs. The first method that we tried was a baseline random search, which just randomly chooses inputs to the simulation, outputs the output of the simulation, and keeps the best result. Now remember that the goal was to minimize the output, so we see that two state-of-the-art algorithms, surrogate modeling algorithms, namely Hyperopt, also known as TPE, and Bayesian optimization with Gaussian processes, these gave better results than random search as expected. Then we compared our method, which gave even better results. However, the variance was quite high, and we hypothesized that this was due to one hyperparameter of our model, this small letter r, which indicates how many random search samples we start with. So all of these methods, they start with just some random exploration, and only then is the surrogate model used. And indeed, when we reduce this number of random samples that we start with, these random initial guesses, we achieved much better results. Not only was the variance reduced, the best found objective was also reduced. So naturally we tried to reduce this number of random samples even further. However, this gave worse results. And this is due to the limited information and the dependence on this first initial guess. What is interesting though is that in this competition there was also a track with unlimited iterations. So instead of limiting the number of iterations to 200, there was no limit. And we found that in one of these 5 runs, because the variance was so high, one run achieved a very good result. So that is the result that we submitted to the track with unlimited iterations, where an objective of around lower than 14 was found. So this was our method, and thank you very much for your attention.